Testing. So good afternoon, everybody. If you could take your seats, it's 1:45, time to begin this afternoon's session. And the first speaker of this afternoon will be Daniel Stenberg. Daniel is a senior network engineer from Mozilla, and he works with Firefox networking. He participated in the HTTP/2 work within the IETF and has hands-on experience with HTTP2 implementations. He's perhaps best known as the maintainer and lead developer of curl. And today he's going to be talking about web transport today and tomorrow. So please, Daniel.
Hey. So, I'm going to talk about trains today. So I found this lovely train image from the past. So web transport today and tomorrow in half an hour. So this is me. As you heard, I do curl quite a lot. I actually wrote my first HTTP implementation basically 20 years ago. I've been doing HTTP since I participated in IETF with HTTP 1.1, HTTP 2, and with Quick now since about 10 years back, and I'm employed by Mozilla. So, web transport is HTTP. So, of course, HTTP is more than web. HTTP is used by a lot of other services today too, but I'm going to focus on the web side of things here, because the web is sort of what the users see, and this is what's going to run through your networks a lot going forward. We started out with HTTP 1 back in the 90s. 99 was the last invention of HTTP 1.1. It has been with us for a long time. We shipped HTTP 2 roughly 2 years ago, and we're going to see something else which isn't HTTP 3, but it's quick. And I'm going to run through this for you. If we look a little bit on some of the trends on the web today, looking at the major websites out in the world, we can see that there's a definite trend. We're going up in volume and up in number of objects over the years. An average site now has more than 100 objects these days. All those objects need a HTTP request one by one to get them, and the amount of data is increasing quite a lot too. And there's no stopping in this trend. It's got to continue like this for more time. And what is notable then is that on average there are more than 50 resources of these for each site that reside on the same domain. I'll explain why that matters. HTTP 1.1 is what I call a round-trip bonanza. It is this ping-pong thing, you know, request and response. That's me and the cloud, right? And the cloud is far away in many instances. There's a long time waiting. I'm sending a request, I'm waiting for the response to come back. Sure, I can open more connections, but each connection has this ping, pong, and that's many hundred milliseconds. Sometimes longer than that, sometimes shorter. So we're waiting for the response to come back, and then we send the next request and response, and the next request and response. Once upon a time, we thought we could solve this in HTTP 1.1, and we introduced pipelining, which means that you can send multiple requests before any response comes back, but that sort of was never deployed. It didn't really work, so we don't use that in any desktop browser today. this is what we do. We send a request, we wait, we get the response back. We send the next request. That's not a very good use of TCP, as you can see. So, we introduce another problem then with, that we call head-of-line blocking. Since we then open more connections to handle this, instead of waiting on one connection, we open more connections. We have more lines in the supermarket. So when you, as a browser, want to send out a request, which line is the fastest, right? When you stand there in line in the supermarket, which line is the fastest? Really hard to tell, right? It's never the one you pick. Sure, TCP-wise, you can always sort of start your own new line, in theory at least, but there's a limit to that too, and there's a penalty for that in resource and time and so on. So a tricky problem for browsers today. Two of the problems with HTTP 1.1 that, of course, crafty people in the world have sort of invented funny workarounds. So there's a long time to the cloud to get back. Ping pong, we have to wait. So instead of doing that a lot of times, why not put all images into one, right? 178 flags in one image. This is not ping pong, ping pong, ping pong. This is one. Ping, pong, a lot of flags. And of course, you only want to show 3 of these on each page, but sure, you saved a lot of round trips. It's really bad for your cache, and you got a lot more data than you wanted, but it's faster. Or you just cram it into the style sheet, like this. It's not very friendly to anyone who's reading this, but this is then, you ask for a style sheet, but you don't only get the style sheet, you get a lot of icons or images embedded in the style sheet. Ask for the style sheet, get a whole bunch of stuff back. Saves round trips. You get a lot of data. Or if you're using JavaScript, get all the JavaScripts at once, right? Because, same sort of spirit. Ask for one thing, get a whole busload back. Saves round trips. We open connections to each host name when we're surfing the web, right? Web browsers open 6 TCP connections per host name. Simplified speaking, but that's basically what we do. So when you want to have more than 6 connections to your website, you just create some new host names for your website, and wham, you have more connections. So if you have a lot of images on your website, some sites do, you just create more host names and you get more connections. This doesn't really scale, and it's really tricky for the browser then to sort of keep all these connections alive, especially when you sort of move around on the site. Which connections are you going to keep alive and which do you have to close? You can't really keep 100 connections for each site alive for very long. So yeah, that works. But to sort of mitigate some of those problems and bring in those workarounds, in sort of stop having them as funny workarounds, hacks on HTTP 1, we started working and we shipped HTTP 2 in May 2015. And with HTTP 2, we tried to create protocol primitives to do the same things that were workarounds, but now they're defining the protocols how to do that. So for example, I should emphasize this then, that we changed how we send HTTP, but we don't change HTTP. HTTP is the same thing, we just change how we transport HTTP. So we still have request responses, we have headers, we have cookies, we have everything you love about HTTP, but we just send them differently. So, for example, then, we made HTTP 2 multiplexed, so we can have one connection, and we can send several different streams over that single connection. Like in this case, we have one image of a Justin train, and we have one image of an IKEA train. And you want to get them over an HTTP connection, you split them up into frames, and you send it over one connection, frame, 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 frame from different streams on the same connection, multiplexed. Justin and IKEA trains in one connection. That is sort of one of the core primitives of HTTP 2 that made made it possible to know, now suddenly we don't need to open all those connections. We can actually send a lot of resources over the same connection, much better in many cases. And this then makes it a lot better. It is using a TCP much better now. So instead of doing this, that's me and the cloud. And instead of, I'm sending a request and I'm getting a response back. But instead of waiting for that response coming back until we send another request, we can send the other request at once. We don't have to wait. We can just fill the outgoing pipe immediately, request, request, request. And it'll send responses back when it has time for it. And in this case, might be one of the requests might be slower, so it might actually sort of end after this second request. We can sort of utilize TCP much better. We can fill the pipe in both directions much better. And we can do these sort of basically unlimited number of streams over the same physical connection. Great. That is what we shipped with HTTP 2. It's now out there, live on the internet, and not that many people noticed, actually. I mean, the transition and the deployment of HTTP 2 has been really smooth and sort of painless for most people. Basically, all servers that you care about support HTTP 2 today. They've been doing it for a long time, too. These are basically a bunch of the open source ones and a bunch of the big commercial ones. So a huge portion of all the server softwares speak HTTP 2 since years back, and all the browsers do, also since way before we even shipped the RFC. So we have the servers, we have the browsers, and now we only need the users to use these things in the right combination, right? So if we're looking at the in Firefox that I work with, we collect, or people can opt in to sort of agree to send in user statistics, so we can actually see how large percentage of all the traffic that is HTTP 2. And Firefox statistics of April this year, 35% of all HTTP is actually HTTP 2. So I'm talking about HTTP as a concept and not as a protocol, and HTTP 2 is a protocol. And this is based on the volume of HTTP. And as you may remember from reading about HTTP 2 before, all the browsers, and in fact all the servers too, there's really no deployment in the world that actually speaks HTTP without HTTPS. So this is the total per HTTP, which means that as a share of HTTPS, and HTTPS is the requirement for HTTP 2. So out of HTTPS on the world today, 70% of the servers that Firefox users talk to are responding HTTP 2. A question there? Sorry, once? Number of connections or traffic volume? This is number of connections, a number of HTTP requests done by Firefox users who are participating in this data. So it's heavily skewed to early users and to mass volume sites. So of course, this means that all the big, Google, Facebook, Twitter, and some others are a big portion of this. And of course, the long tail is not a big factor here. So that taken into account, I think 70% is still a large number. If we look at it from the other end, we can see that if we're just scanning the top 10 million sites in the world, 13% of them run HTTP 2, and that has doubled the last year, which I think is fairly good, still sort of far away from even half of the servers in the world. Looking at the top 1,000, we're approaching 1/3. And of course, if you deploy it on your site, or I deploy this on my site, so I have 90% of my visitors using HTTP 2. That might not be true for everyone. You may not get exactly 90%, but all the browsers support this, so most of your users will go HTTP 2 if you just let them. So that was sort of HTTP 1, the problems, and then we did HTTP 2. HTTP 2 had some new fun things, and then we deployed it, and a lot of users are using it. So what did we sort of get out of that 2 years down the road? Was it good? Did anyone sort of get happy with that. Some did, some did not. This is numbers, also again measured from Firefox. From the really remote corners of the internet, we should look at the bottom of this table. Round trip times to the site you're communicating with, the 95th percentile of Firefox users. They're roughly a second away. That's a long time. Request, response, 1 second. And of course, if you're waiting for each response to come back before you send the next request, that is a lot of time. I mean, watching a regular website in this situation, that's painful. Going HTTP2 here is making things a lot better for these users. We're gathering queuing time in a Firefox. That means sort of when Firefox, the browser, wants to send a request to the site you're browsing, it puts the outgoing request in a queue to wait until it gets sent over the wire to get the request. That's the queue. It sits in the queue, and then it gets sent out over the network. So we can see then how the queuing time has changed from HTTP1 to HTTP2. Of course, sitting in the queue, a shorter time is a better situation. Here we can certainly see that for the worst cases, 2 seconds waiting time, down to 16 milliseconds time, on average in the 95th percentile. Again, this is the really remote corners of the internet, where you're probably on some really, really lousy wireless networks. But still, this is a huge improvement to those users. We can also see then that the percentage of requests that are sitting in the queue for longer than 100 milliseconds, that's the number in the bottom, sort of has drastically decreased. So, if you're having a really shitty internet, H2 is really, really the solution for making things better, or at least according to some metrics. Here's another metric. Here's a fun, this is a slide I've stolen from Fastly. Human made an excellent presentation. You should Google if you want to see more specifics about this. But he's basically measured how H1 and H2, HTTP1 and HTTP2, compares with Firefox and Chrome in different network situations. And we don't have to care about the details here properly, but we can see if we're looking at speeds here, we can see that the blue line and the red line, the blue and orange is Firefox, red and green are Chrome. Blue and red are faster than the other ones. H2 wins in the 0% packet loss situation. That's sort of the key from this slide. 40 millisecond latency. So this just shows that, yeah, if things are good, fairly decent latency, no packet loss, H2 makes your sites faster. 2% packet loss, not so good anymore. 2% packet loss, of course, is an awful lot of packet loss. So that's not your typical Wi-Fi or whatever, it's a really broken Wi-Fi. But it still shows you that, wham, suddenly H1 is much better than H2 for both browsers, and by quite a margin too. Not a good situation, or as I would put it, a sad face. This is clearly the worst case for H2. And this is where one of the reasons to start looking at why is this? Well, we have one connection instead of 6. Packet loss for one connection, of course, that hits that one connection and all the streams. It's not just 1 out of 6, it's 1 out of 1. It has to sit there waiting. That makes it a header line blocking, so one packet loss means everything waits for that packet to sort of get resent, reappear. With a 2% packet loss rate, that's a lot of waiting for a lot of streams, possibly 100 streams or more. So as you remember, we have this is sort of TCP/IP, and there's a TLS and there's a H2 on that, and there's a train. Well, there are two trains, the Justin train and the IKEA train, right? And when we lose a packet somewhere here, they're not aligned, right? When we lose a packet somewhere, everything has to wait so that we can repair the streams or the connection and we can go on with the trains. Not really what we want in a 2% packet loss situation. So we want to fix the TCP header line blocking. Right, how hard can that be? Someone did this. Well, a non-blocking TCP TLS HTTP2 implementation, right, with independent packets. So each packet that you lose, they have to sort of be stream aware so that you can lose one packet and the other streams can continue. You don't have to wait for that particular packet you lose, right? But you can't do that with TCP because it's a stream, it's not packet-based, you can't do that. So we need something to sort of do that, re-implement it. Maybe we should do a new TCP or change TCP. Well, you know as good as I know that we don't deploy new protocols. We don't do new transport protocols because TCP and UDP are basically the only protocols we can deploy today. So basically that's sort of out of the debate. So we're making a new protocol instead on top of another protocol like UDP. Fixing TCP or changing TCP, that could be done, but it's a sort of a very, very slow process that is take ages or decades or whatever. TCP fast open is an excellent example of a change that takes forever to actually get deployed in the wild, or if it is even doable. So doing this in the real world today is called QUIC. QUIC is a protocol that is implemented and deployed widely by Google. It is basically what I said. It is a TCP-like thing with crypto and H2 frames over UDP. And the entire thing in user space, in the browser and in the server. It is using end-to-end crypto. It doesn't reveal much of the actual underlying things to anyone who want to interfere with it. So with this, you don't get any TCP header line blocking. You actually get independent streams that are actually, you can lose a bunch of packets in one stream and the other streams can go on. Changing things on this in this layer also introduces new fun things that you can introduce zero RTT connections. You can actually start a new connection without any round trip sort of ways to the handshake time to get a new connection. You get a zero RTT if you had a previous connection with the server. But it sort of fixes a lot of other, you can, when here, you can fix a lot of other sort of issues you get with TLS and TCP. And it makes it a busload of, magnitudes faster. If you happen to be a global company with a huge market share, you can just fix client side and server side at the same time and iterate really, really fast. And yeah, it works. Google QUIC is today 7% of the internet data traffic. Now. If you're using Chrome now, you're using QUIC already. It works. Again, QUIC maintains, is also sort of like H2. It maintains HTTP semantics, same things, request, response, headers, everything, just changes how it is transported. So instead of being disaligned, it is aligned. Losing just the Justin car, the IKEA train can continue. So the Google QUIC is now converted into the IETF, or taken into the IETF, and there's becoming an IETF QUIC. So it is going to become a standard, and this is going to become something that we're going to see deployed from more companies than just Google really soon. Maybe in mid this year. There's going to be a interop draft in June, hopefully. So this is not HTTP3 in anything, in any name at least, but it's basically what it's going to become. And it's not TCP2 either, even if some of us thinks of it that way. It's just Quick. And that's the official logo for Quick. That's what I wanted to tell you about. Thank you.
Okay, do we... We have 3 or 4 minutes if there's time for just a couple of quick questions. Quick questions being the British terminology. Can we have the microphone over here, please?
Hi, Christian Larsson from Deutsche Telekom. So, are we done now, or are there more things to fix? Will there be a Quick 2 or an HTTP form, whatever you might want to call it?
Given how we came to this point, I would say that no, we're not done. But I don't think anyone is looking past Quick, and Quick isn't really done in any way or fashion either. The Google Quick is being changed quite a lot in the IETF, so we're not really sure what the IETF Quick is going to be. And sending H2 over Quick is just the beginning of Quick. Quick is going to be used to send other transport protocols too. So I think Quick is the beginning of something that is going to go on for a longer time, and it's going to be much more than just H2.
Okay, so I'm also curious about the changes that are going in. I mean, you mentioned here you had Google Quick, and you're saying IETF Quick. What are the, I mean, from a very high level perspective, kind of, are there technical improvemements, or is
there is a lot of changes. I mean, if you want to get 150 emails every day, subscribe to that GitHub repo. It's an insane activity. But for example, the Google Quick has its own crypto, and the IETF Quick has TLS 1.3. That's a huge differentiator. And there's a lot of discussions changing every single packet headers, negotiation. Yes, I don't think there's a single bit that remains the same in that one as in that one. They're both called Quick, so they're sort of hard to differentiate that way, but there's going to be a lot of polish and tweaking to get sort of Google's mindset sort of converted into how it should be as a standard.
Okay, is it a quick question? Yeah. Can you wait for the microphone? Sorry.
Quick question.
Yeah, there's room for a lot of good puns or bad puns.
No, but is there follow-up on that? Are there any major conceptual differences between the Google Quick and the IETF Quick? No.
The major conceptual differences is that the Google Quick was made to send H2 only. It's an H2, they sort of squished all the layers into one. We send H2 over UDP, magic happens. But when they took it into the IETF, they did that under the condition that no, we're going to do this for more than H2. So now the conceptual difference is now that it's sort of split up now into a transport layer and sort of an application layer within Quick. So you can send H2 over the transport Quick. So you should potentially send DNS over Quick or whatever over Quick transport.
So IETF Quick is turning into TCP, new TCP over UDP.
It is turning into TCP and a transport layer above it, yes, and TLS. I think I'm out of time.
Yeah, I think is it a very speedy question? Okay.
Quick, ask Quick.
As I understand, Quick it's mem from Netnod. As I understand, Quick is on top of UDP. Is there any thoughts of having it just on IP directly, to have it as a third protocol or so over IP?
Well, no, because that's sort of all the NASA firewalls are saying no. So they're just stop, don't do that. So no.
Okay, I'm sure Daniel will be around to answer more questions, but for now, can you thank him for a great presentation? Thanks very much, Daniel.
Thank you.
Thank you. Thank you very much. So while she gets the microphone treatment from Henrik here, I'm going to introduce our next speaker of today's session. It's apologies in advance if I mispronounce the name. I'm going to give it my best shot. Caroline Puygrenier. Fantastic. I've been practicing that all day. From one of our meeting sponsors, actually, Interxion. She is the Director of Strategy and Business Development Connectivity segment. She is responsible for the strategy and business development of Interxion's connectivity segment, and she's here today to talk to you about the role of the highly connected data center campus. So please give her a warm welcome.
Thank you very much. I hope you can hear me, okay, because it's not made for long hair, this microphone. So today we've heard a lot about the networking side of things, and we wanted to go back into a little bit more details of where we think that our data center fit in that whole interconnectivity. So if you look on the right-hand side of the slide, you've got, obviously you can see clouds, which is the new technology, but the old way of transporting data and the best way to transport data was on USB sticks and so on and so forth. Why we think that data center are so important these days and where we think we fit in that world is we've heard earlier on about how important the millisecond of round-trip delay is, and having carriers, networks, eyeballs, communities, clouds, and everything in one data center makes the interconnectivity, the round-trip delay, and so on much faster. So when you look at what we see ourselves as a shipping company. So we help the content providers, the network, content delivery network, and so on, to put everything together under one roof. So everything going mobile as well at the moment, so we also work quite closely with mobile operators to get all that traffic shipped across. So we wanted to give you a bit more background, obviously being with Netnod and working quite closely with Netnod, to give you a little bit more background on where we see ourselves fitting in the Nordics. So we have, as you can see, we have 11 countries where we're present, 13 cities, and we have a few stronger points than others where the connectivity and where the content/traffic is exchanged. So Frankfurt is our number one location in terms of carriers' presence and traffic being exchanged. But Stockholm is a very close partner for so on, and also is a very important location for us as being a gateway to Russia, to the Baltics, and also to mainland Europe and the rest of the world. As we can see, within less than 30 milliseconds, we can reach over 80% of the European GDP market. So just to give you a bit more background on what I mentioned about the gateways, so we have a few gateways, as of what we call gateways in our market, where we see the focal point of the traffic being exchanged. So our number one gateway is a place called Marseille in France. Nothing to do with the fact that it's a lovely city, because it's unfortunately not very nice. But a lot of sea cables are landing there. So there's a new model of sea cables, which is what we call open access sea cables, where instead of having one landing stations, very expensive backhaul cost to then go and use the capacity on the sea cables, there's two new sea cables called CME-5 and AAE1 that land in those facilities, and you can just literally, with a cross-connect, go and connect to the sea cables. So reducing the round-trip delay quite a lot, but also the cost of accessing the sea cables. We have a place called Vienna, which has been a quite focal point for our Central European partners, where we exchange quite a lot of traffic between, so the Serbian, for example, Internet Exchange is present there as well, and so on. So that's quite important. Dublin, of all places, I'm sure you're all aware, that's where most of the big content providers landed in Europe as a first start. Nothing to do with the fact that European Union gave them a very good incentive on tax, but that was one of the first points that they landed. And obviously the most important one, and what we're here today, is to talk about Stockholm. So Stockholm is, for us, we see that as the gateway to Russia, but also the gateway to the whole of the Nordics. So we have a presence in Copenhagen, but we see Stockholm, and I'll show you in a minute with some statistics. We see Stockholm as a crucial point of exchanging traffic, but also traffic being generating from Stockholm and then going to other places. So with further ado, I will bore you with some statistics. So this is all traffic on the routes between Stockholm, Copenhagen, Stockholm, Helsinki, Frankfurt, Moscow, Amsterdam, and London. We can see there's a very high peak around 2014, which is when we saw a lot of content providers suddenly realizing how important the Nordics were, and they decided to choose Stockholm as the main point of place to actually settle for traffic distribution in Europe, in the Nordics. So as you can see, the colors between London and Copenhagen are a bit blurred, but as you can see, the traffic exchange with places like Moscow is growing rapidly and so on, and that curve from 2014, as I said, is quite crucial. So this is per city, and the next graph is per regions. So we can see Stockholm, the importance of Stockholm for the rest of the world, and how quickly the traffic growth is coming out of. So we got the statistics from telegeography. We tried to get it from some specific carrier partners of ours, but information be quite sensitive, so we got that from telegeography to share with you today. So the other comparison I wanted to make is, I mean, we heard today about Netnod and Copenhagen as the second point of presence, and we are also present in in Copenhagen, but the difference in terms of traffic is quite important. So you can see that the majority of the traffic generated out of Copenhagen goes to Stockholm. So Stockholm is still the main point of traffic exchange for that. And the growth out of Copenhagen is not quite as significant as the rest for us out of Stockholm. And the last part, one of the last parts is also per region. So again, traffic generated to the rest of the world is out of Copenhagen is quite important. So I'm not going to take the whole of my time, which is good because people then can ask a few questions, hopefully, and then we can run ahead again like we did this morning. But what we want to remember out of this graph is, as I said, how important Stockholm is in terms of a focus for us as a data center company to work closely with carrier partners, with internet exchange partners, because the content providers, the carriers and so on are exchanging huge amounts of traffic from those locations. So our CEO is aware of all those stats and sees Stockholm as a very important point. We keep growing. We have Stockholm 5 now as a data center, and the growth is quite significant. So what we want to remember out of Stockholm is the content providers, as I mentioned, are moving to Stockholm as a priority. But we see Copenhagen with the work that Netnod is doing with comics being rebranded and so on, and try to attract more of you as networks and so on within Copenhagen. I mean, we work with a local internet exchange, which is not quite as active as Netnod, I have to say. So we see Copenhagen as the next place where the traffic growth will be arriving. We get on a regular basis now requests from content providers to settle down in Copenhagen, which hopefully will see a similar trend coming out of Copenhagen in the near future. So, I mean, I don't know if you have any questions. I mean, data centers are quite sort of the background in terms of where the traffic is generated, but we would not exist without partners such as Netnod, all the big carriers that we work with. So it's a quite close relationship with as I said, with all of you, hopefully in the near future. So any questions you have for me? No? Anything? Okay. Perfect.
Okay.
Thank you very much.
Thank you very much. So back ahead of schedule again. Do we have Amanda from Spotify? Oh, there you go. So Amanda Östlund, these names are really getting to me this afternoon, is a network engineer at Spotify, and today she's going to be talking to you about content delivery at Spotify. Once she gets the microphone up and running.
How about that?
Perfect.
That works.
Great.
Cool.
Thanks, Amanda.
Thank you. I have a quite small head, so I always have some trouble with these. All right. Sorry, I'm thinking I'm actually gonna. I'm not too keen on these.
So while we wait with the little technical blip, just a few quick announcements. Just out of interest, who's going to be coming to the social tonight by a show of hands? Yeah. Oh, wow, very enthusiastic. I was told to mention that in case any of you want to store any important bags, laptops, heavy items, there's going to be a safe room behind there if you don't want to take it to the social tonight. So if before the buses leave, you find one of the Netnod support staff, we can store that for you if you don't want to risk breaking or losing your technology. Of course, you would never do that. Let me think if there's anything else while we sort this out. Yeah, by a quick show of hands, who was aware of Quick before the presentation this afternoon? Okay, so, okay, not everybody. By a quick show of hands, who has more questions about Quick that they want to ask now that they've seen the presentation? Or did everyone manage to get their questions in within the time? You have one more question? For later. Yeah, no, not for now. Just out of interest. Okay. Okay. Let me see. And I think we might be almost ready. Okay, then one more quick poll, just for my interest. From the lunch today, I would like to know who had the pork, by a show of hands. Who had the seafood? And who missed the vegetarian option? Okay, very few there. Yeah. It's these important issues that I'm here to discuss today. So, ladies and gentlemen, the technical problem has been solved, and I hand you over to Amanda from Spotify. Thank you for your patience.
Apologies about that. So, hello everyone. So yes, my name is Amanda, and I'm here to talk about content delivery at Spotify. If I haven't missed something this morning, I believe this is about the third talk about content delivery. So I see a trend. I will be taking some questions in the end of the presentation if we have some time, but otherwise you will be able to catch me during the social this evening, and of course during the coffee breaks and so forth. I have a background of computer and system science at Stockholm University. I work as a network engineer at Spotify since about 3 years back. Since about November, I work in a newly formed team entirely focused on content delivery. Prior to the formation of this team, I worked with Spotify's data centers and with some CDN and peering. So before we start off, I would like to mention a few things about Spotify itself before proceeding to briefly explain what happens when you press play in the Spotify client. I will give you a glimpse into the Spotify control plane and how we use it to ensure good quality for end users. I will also talk about why we have pursued the notion of building our own CDN alongside the use of public CDNs. And of course, I'll mention some about our own caches. So I suppose you might have heard of a small little music service called Spotify. It's both a free and subscriber-based on-demand service with music, video shows, and podcasts. It's widely available in 60 markets with an active user base of over 100 million. Quite small, isn't it? So you got your Spotify client installed. What happens when you press play? I'm not going to go into the whole chain of events here because quite a lot happens, to be honest. But let's look about how the client fetches the requested content, because that's what we're here for, the content delivery. So when a client logs in, it will be given a set of URLs. These URLs are often public CDNs, and they are places where the client can fetch head files. Head files are a bit special. They are the first few seconds of a song entirely unencrypted. And they are there to serve a purpose and solve a real problem. To play a song, the client needs to exchange keys before it can play the song it's requesting. Thanks to the head file, the first few seconds of the song can start playing while other things happen in the background, making the playing seem instant, regardless of whether the song is previously downloaded and saved in the client or pre-cached. In other words, it's a mask for latency. Also, meanwhile, the head file is fetched. The client requests the control plane for another set of URLs for the actual set of files it wants, which in this case would be the rest of the song. These URLs, which the control plane responds with, points to entirely different CDNs, both public and private CDNs. So the control plane actually consists of several different services, but together they determine where to send our users. So what do we want the control plane to do? We wanted to hand out the URLs I mentioned earlier when a client plays a song, but not only that, we wanted to hand out the URLs in a clever way to make sure we utilize our private CDN. It all starts with the BGP sessions between the peer routers and a PMAC process. We use the BGP functions of PMAC in order to collect all the BGP routes learned through peering sessions on IXs and PNIs. These routes are collected and compiled into one global route table. And here we have swapped a few metrics around. For instance, we listen to AS path before MED, before local pref. But this only happens over peering links. There is a little war story here that I might be telling you tonight if you're interested. So now we have all the routes, and we know who we peer with, but we need some more information for the control plane. We need to be aware of where our caches are. We also need to know the capacity of our links and what type they are. For instance, if they're transit or an IX link or a PNI. So this is information we just feed manually into the system. So we finally have our routes, our peers, location of our caches, the capacity of our links, and what type of links they are. And now we can let the system determine where to send the users as follows. Is there a cache in the area? Are we peering? What link shall we use? Links will be looked up in the following order with PNI, public peering, and then transit. Do we have resources in the cache? A PNI will always have priority over everything else in a cache. Do we have resources on the link? If any of the points on this list is answered with a no, the user will be giving a link to a public CDN instead. So I mentioned that the control plane takes resources into consideration. So how do we do this? We actually collect RPS, requests per second. And that's good enough for us to figure out traffic levels. Originally, we wanted to collect this information from the links on a network level. But we ran into some design issues with oscillation and feedback loops. But in practice, RPS turned out to work really great. A luxury we have as a content provider is that we really know our traffic. The result? So here we see a traffic curve, and this is not RPS, this is actual network traffic. The flat pillar you see to the far left is when this particular POP was intentionally set to a lower target utilization. So you can see how flat and nice the top of that curve is. So on to our next topic. Why build our own CDN? Public CDNs work well, and they have a worldwide reach. Our first metric is cost. By putting some of the traffic on our own CDNs, we can lower the cost of serving users. But another reason is to support growth, and this metric goes hand in hand with the cost. More users equals more traffic. So if we can put some of that traffic on our own CDNs, we're happy. Another reason is that we can be more in control of our content delivery. We can selectively route traffic where we want it, and we can have dedicated capacity. Also, that we can control exactly what we want to cache. We know our catalog better than a public cache. And this also means that we can fill our own cache with only our content. And having our own CDN finally also allows us to collect more data about our content delivery that we could, in an attempt to improve the content delivery. So our own CDN, they're built in partnership with Fastly. We use two different configurations from Fastly, and internally at Spotify we call them a megapop and a micropop. All of our POPs are connected to a peer router. This means that if you peer with Spotify, you peer directly with a cache. The micropop is just one server, but it manages to store most of our popular content. People actually listen to quite the same music. They might think they're hipster, but they really aren't. You'd be surprised. The megapop is scalable and has more storage. Our configuration has 4 servers. It serves all music, so not only popular music. And that picture is not a picture from Bromma. Usually, you can see the actual caches in the bottom of the rack. Normally, they will have pretty red faceplates. They might be coming for this pop as well, I don't know. We're actually approaching the end of what I have to say today. But I do have some shameless self-promotion left of why you should peer with Spotify. Thanks to our control plane, you can ensure good quality of our mutual customers' Spotify experience. Also control, because we will do our best to accommodate your needs. We really want to make our peering partners happy. Peering with us will also lower Spotify traffic from public CDN. Keep in mind that if you peer with Spotify, you peer directly with a cache. I also want to show you this. This is a map of our current and upcoming CDN pop locations. We are present or to be present in all of these locations, so US, Europe, and APAC. So I was actually thinking if somebody had a question, maybe we could take that now. Some head scratching now. All right, so a little summary then. So we have a hybrid solution here with 1 private CDN and 3 different public CDNs. Right?
Thank you. Do you collect statistics for breakage from the client? You had a few different ways and a few different URLs and so on. Does the Spotify client report this in, and you do analysis on that data so that you could tell if things are broken, how many times it has to go to the second URL or that kind of thing, and you map this and report that to ISPs, or is this data? Would be very interesting to know how well this works as an ISP, to know what the customer experience is.
Data is definitely collected, and essentially what's important then with these files is that when a client fetches something and the response is the response timer is just really short. So the client times out super quickly if it doesn't get a reply. So we'll just move on to the next URL really quickly without end users noticing at all. And we do. I can't really think of how this is used really in monitoring or anything. I'm just thinking monitoring terms here. But all data is definitely collected.
Yeah, because it would be interesting if one thing persistently fails over time, that can be fixed. So that, and also if if one resource is constantly, I don't know, the latency is higher or whatever, to collect that kind of statistics, or if a customer has packet loss and it actually all the connections are very slow or something like that, to understand that this is going on.
Yeah, that is something we could, for instance, figure out with that data. See if we see some persistent failures from an AS number to a cache, for instance, and that could be one of those situations where we would take the decision to send those users to another cache somewhere else, where they get better performance.
Yes, that's working around the problem. What I'm talking about is showing that this path that we thought was the best path is not, and there might be a problem there. If you're constantly just working around it, it's never going to get fixed.
Oh, so you mean if we would have a conversation with a peer partner then and try to solve this?
If there is a channel, so if there is a way for you to tell the ISP that constantly this path is always seems to work really badly.
Yes.
We're working around it. Customer doesn't care, but you might want to look into that.
Yes, of course.
Okay. Second thing, IPv6.
Yes. Well. Where is Mr. David Barroso? He's not here. Well.
Working on it.
Yes.
Okay. Thank you.
Does anyone else have any more questions? We have a microphone over here, please.
Is this working? All right, cool. Hugge, NORDUnet. So, I mean, I guess regarding the IPv6 thing, will you not be able to do V6 before Fastly does it? Because I know that Fastly is a bit behind on V6. Is these solutions so tightly tied together that they don't work? I mean, you can't. They have the same feature train essentially, or since this is an in-house Fastly type of CDN or Fastly style CDN, or how is the relationship really here between Spotify CDN and Fastly CDN?
Well, they essentially build their caches, and they're also the systems of how they work, sort of. So.
Right. So that means when Fastly has V6, Spotify has V6.
Yes.
All right. Cool.
That's a little bit how it works.
Do we have any more questions? We've got a little bit more time for Amanda. Anyone got anything they want to ask? V6 related or otherwise? No? Okay, well, thank you very much. Please thank Amanda for us. and you may receive your bag. So the next speaker really kind of needs no introduction from me. I'll do it anyway, though. It's Patrik Fältström. He's the head of research and development at Netnod. He leads the Netnod's long-term projects. He's the chair of ICANN, Security and Stability Advisory Committee, and has been appointed advisor to the Swedish government on IT-related issues in 2003 and ever since. So it gives me great pleasure to welcome to the stage Patrik Fältström.
So thank you. That was not the first slide. That's right. My fault, sorry. There. So I'm trying to do, nice to see so many people. Hello. I want to show this one, because I work also with NTP stuff. I'm not going to talk about it here. That's correct time. Cool stuff. And yes, it's doing the daylight savings correctly. Anyways, back to what I'm going to talk about. I'm actually going to talk a little bit about some background issues of where I think we are in Sweden and the world. And this is very much sort of evolution of policy. And what I've been doing, which is sort of the formation of this presentation, is that I did some digging why we people really want an open internet. And what I've found is that this starts actually 538 before Christ. And does it go back that far? It actually does, because this is a clay cylinder that the Persian king, when invading Babylonia, after sort of running them over, and of course that's something we are pretty good at in human history, to try to kill each other, take over each other's land and cows and pigs and whatever we have, to grab food and whatnot. So what he did here was that on this cylinder in clay, that was the first time when sort of the king or the ruler of a country started to recognize the individual people that are sort of inhabitants in the country. It was a good thing to have people as part of your country. More people, more wealth for you as a king. We can then move forward to 1215, which is sort of what people think is the origin of, this is Magna Carta. And this is the first time when people said that, okay, wait a second, it's actually very important for people to be able to say whatever they want, to be recognized, to start to elect your own leaders, and to be able to sort of form groups and cultures, and yes, we are different, we do think different. So that's good so far, but then another thing happened. In 1439, we had Gutenberg that actually came up with the printing press. And this was kind of interesting because for as I just showed you, for a couple of hundred years, we have been thinking about how important it was that we all were individuals, we were going to think, would do whatever we want, and that's, of course, very good for a leader until we as individuals could spread the word. So when the printing press arrived, that was really bad for the leader. Because suddenly we could write on the paper and say what we thought a good world would look like, and we could mass produce that material and distribute it. Downhill from there. So in 1766, and this is the reason why I made this presentation in December last year, or like a different version of it, this is a newer modernization. Sweden got the first law in the world that is the freedom of expression. This made it possible, tryckfrihetsförordningen, this made it possible for people to actually, this was a law that said people are allowed and they should have the right to be able to say whatever they want. 1766, so if you go back here, we see this was 1439. So it took a couple of hundred years before we got the law that said people have the ability to think whatever they want without ending up in prison. Of course, after 1766, it went downhill from there. the king invented all different kind of legislations that were like including lots of censorship and the ability to block things that are printed and all different kind of crap. In France, we had the Declaration of Freedom, very well known. Sweden, it went worse and worse, until something happened in 1830. We got the first newspaper. At this point in time, it was basically illegal to talk about anything that the government in Sweden did. And Aftonbladet, as a newspaper, invented two things. The first thing that they came up with was something called a journalist. It didn't exist before 1830. The second thing they did was that Lars Johan Hierta, that started Aftonbladet, he was thrown in prison because he printed things in Aftonbladet that was illegal. So and the newspaper was torn down and closed. So he started Aftonbladet too and came up with all different kind of names of Aftonbladet, because the legal system made decision in court, you're not allowed, this newspaper is closed, you're not allowed to run it, and then he started a new newspaper the next day. He won, so we managed to actually get some more freedom in Sweden. And then in the world, in 1948, finally we got the Universal Declaration of Human Rights. This is still what we are basing a lot of the thinking in the world, and specifically Article 19, which says that people have the right to express themselves, participate in the society. And a lot of the work, not only legislation, but also corporate social responsibility and other things for companies, is based on this Article 19 of the Universal Declaration of Human Rights. So this is where everything is coming from. What we should remember, though, is that the human rights and everything that we agree on in the United Nations, in reality, are only agreements between countries that states promise each other that they should do, either to protect their citizens, or they promise other countries that they will not do certain things towards their citizens. So human rights have nothing to do with companies, regardless of what people say. Human rights is something that are promises between countries. So this was a big thing in 1948. In 1968, we started to see internet. And of course, we in this room, it's not very difficult to sort of see the difference and understand the difference between the web and the internet, but we just have to read some articles and you see the difference. I'm happy to know both of these guys, and these t-shirts exist in only one of each, and you understand why. Tim Berners-Lee and Windsurf. In 1981, we still had these cars in Sweden. And people not being in Sweden, this is only 35 years ago. This is what we should remember. So my whole point here is that we have been working on this since like 500 years before Christ, and we end up in this. We have a monopoly. They provide the services. They provide the TDM-based communication. They sold the end equipment, and it was in the newspaper when they released a new phone with a new color, and lots of people, including myself, were lining up blocks and blocks of lines because you wanted to have a red phone instead of a blue phone that your neighbor had. And the most fascinating thing was when they released a new service, like hashmark 21, hashmark number, blah, 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 blah. Today, we get sort of a new service in App Store every fraction of a second. And by the way, we didn't have any regulator, and this company was owned by the government. How could we end up there? In '86, we started to get some competition. Here in Sweden, it was not illegal to start radio-based communication companies. So we had this Stenberg that invented, gave the ability for anyone to have a radio and happen to have a touchpad so you could actually dial a number within that sort of radio system. But of course, you were not allowed to connect that, what is now cell phone system, to the telephony system that was run by the company with the orange cars. So they had a human sitting there, so you could request connecting your radio call into the telephony system by having an assistant saying, yes, I'm going to do this, connect you, plug in, blah, blah, blah. Then after a while, it was easier and easier for the human to sit there, and you had to have a human assistant. So at the end of the day, you had a lamp and a button, and whenever you had someone making a call to the phone system, the only thing the human did was to press the button. That was the way of getting around the legislation. And then, of course, the second cell phone company was created, etc. So we started to get some competition. This was only 30 years ago. When we started to get competition, there was also a need, of course, for people to keep their phone number, to change from one telco company to another one. So we had legislation on number portability. We started to have more than one company selling phones, not renting them. We had more than one cell phone provider. In '89, we had, how many people here were working with the internet in these days? I recognize a few people. So I was working at the KTH in these days, together with some of you, and in September '89, we got the satellite link to John von Neumann Supercomputing Center. This link was not full. It was a 64 kilobit link. Of course, it was before libcurl. That's why, before Spotify. So, anyways, cool layer 2 network. And if we look in Europe, these were the only IP networks we had. In Germany, it was illegal to run IP packets. So each university had to have their own satellite link. This is not many years ago. So you had internet in the Nordic region, in Netherlands, in Italy, and Switzerland. In '96, we continued to sort of try to change things here in Sweden. And you recognize some of the people, and some of the people are here. We were a little bit younger then. I blame the aging of the paper to create such a pictures. Anyways, so what this was the group that decided that we actually thought it was a good thing if people could decide on domain names themselves. KTH didn't want to deal with domain names. We didn't want the government to take over. So this was the formation of the Stiftelsen för Internet Infrastruktur, the ones that run the .se top-level domain, and also Netnod. So LM Jogbeck. Anyways. We had no responsibility. We were making decisions. How could we? But politically, things went better and better. So I claim that in 1981, that was from 500 before Christ, it was pretty good. And in Sweden, for 240 years, it went down. And now it's actually getting better, I hope. In 2012, Sweden took the initiative in the Human Rights Council to decide upon this. Remember, you can read it yourself. The important thing is that in the United Nations, this is what countries promise each other. So all countries and all members of the United Nations, which unfortunately is not all countries, but of course that depends on how you define country. It's actually, if you don't have anything else to do, read the Wikipedia article on what is a country. There are about 30 or 40 territories, which the question is whether it's a country or not. Anyways, so what happened here is that countries say that members of the UN agree that it recognizes the global and open nature of the internet as a driving force in accelerating progress towards development in its various forms. So Sweden managed to push in the United Nations that countries recognize that open internet is important for growth. It's a little bit unfortunate that not every, for example, city in Sweden have read this and understand this, but anyways. Should we try a video with audio? Händer inget. So there's no audio. Anyways. Blah, 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 blah. Okay, let's move on. So what else has happened regarding decisions? It was the statement of Carl Bildt, our then foreign minister, when he made his final argument before the vote in United Nations. So So what then happened is that in I think 2001, the Swedish government decided to give a subsidy to build out of fiber, or rather build out of broadband. And that was sort of a mistake. I was helping the Swedish government in 2003. Yes, I failed. It was not so good. But on the other hand, I tried to clean it up. And together with some other people in the room, we managed to change the rules in 2008 to make sure that it was very explicit that the money that was given out is given to investments in passive infrastructure. Of course, a lot of people and a lot of citizens didn't understand and didn't notice this change in legislation and rules in Sweden. So ultimately, in 2014, the Swedish regulator wrote a summary of this is a clarification 6 years later, saying this is actually the rules. So it says, blah, 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 it must be an open network, can be used by multiple operators at the same time, and it says explicitly here that it must be open on the passive level. These have been the rules in Sweden since 2008. You must be able to rent fiber that has got subsidy. In 2016, the regulator is telling Telia, you're not allowed to sort of differentiate priority for various services. So things are sort of getting better, isn't it? And the National Audit Office in Sweden, they have been looking at the digital infrastructure in Sweden, and they have been looking specifically at the deployment of fiber. Their report on the fiber build-out will arrive, as far as I know, May 16, May 17 this spring. So in a month, we will see what the National Audit Office is saying regarding fiber build-out. And what they're looking at is, have people follow the rules? Have there been an audit? And have whatever the Swedish government decided been implemented correctly? And by the way, has the decision Swedish government did, has that helped Sweden as a society to reach the goals that the government has? Which basically means, did the government make the right decisions, or should money has been spent on something else? So we'll see in May. So here it says, planned publishing in April 2017. It will actually be mid-May. But then we have in 2017, we have this decision that says that B2 broadband must block the access to certain services, certain IP addresses, and certain URLs. It also says a couple of other things which are a little bit scary, that anyone can go to any communication provider and request them to block communication, if I exaggerate a little bit. And then the decision that I said between Telia and the regulator, Telia went to court and said, we would like to have this discussed a little bit further. Okay, anyways, doesn't matter, I can explain this. And what the court said was that Telia was right, and Telia do not have to follow the decision by the regulator. So this is going into court, and we'll see what happens. So it's still unclear whether the regulator is correct that Telia can do various prioritization or whether they cannot. So this is still an ongoing court case. So what actually happened now these last couple of years regarding oversight? You saw this nice picture with me and LM and others. Here in Sweden, we started the SWIFTnet in March 1, 1991, the first commercial provider, and Telia came with TIPnet just a few months later. Netnod and NIC-SE started in 1997, but the interesting timeline was in the US, because they, just like in many other countries and just like us in Sweden, did also go through the same kind of thing to move a research network into be privatized. So National Science Foundation was funded by the research agencies within the Defense Department and National Science Foundation. National Science Foundation, basically like Vinnova in Sweden, is probably the closest you can get. There was a cooperative agreement written between National Science Foundation and Network Solutions in 1993. And this is just because someone had to do the operations. So they literally issued an RFP, and Network Solutions said, okay, we can run the DNS. At the same time, we had John Postel in the University of Southern California that was managing IP addresses and stuff. And the job that John Postel had was basically do IANA, manage top-level domains IP addresses, one person on his spare time. And this was part of the so-called Terranode contract with DARPA. So National Science Foundation didn't want to touch things, and DARPA didn't want either. They took a step back. So there was this internet thing, so what should we do? So this hot potato ended up with Department of Commerce and NTIA. So this was just like what happened in Sweden when KTH was releasing their interest in what we did in the internet. The same thing happened in the US. So suddenly ended up on Department of Commerce and NTIA. So, and at the same time, Network Solution was allowed to start a charge for domain names, $90 US per domain name a year. And they had the monopoly. So that was quite a lot of money. So it was some economical interest of actually running domain names. So John Postel created an ad hoc committee and published the new registries and delegation of international top-level domains. And in 1997, there was an MOU that a lot of individuals and organizations signed. Specifically, it was Tele2 and Telia in Sweden that was participating quite a lot on this through me and Amar Andersson. So there were a lot of signatories on how to move forward, but unfortunately, this was not implemented. So in January 28, 1990, basically nothing happened. In January 28, 1998, John Postel and the root server operators, Lars-Johan Liemann, he's not here, right? No, he's not here yet. Anyways, they had a discussion on whether the root zone should be copied from VeriSign or whether it should be copied from John Postel. And the root server operator said, we trust John Postel. So they started copying the file from John Postel instead of from VeriSign. I was in Washington that day, and I was called to Department of Commerce the morning after. Bloody hell. So the good thing with that was that now suddenly the US government understood we better do something. So in February 1998, just 2 weeks later, the green paper was published that talked about multi-stakeholder processes. It was out on public consultation, and in 1998, in June, the white paper was published that talked about something called ICANN. In October, John Postel proposes the creation of ICANN to NTA, and then he died. November, ICANN is recognized, and on December 24, ICANN took over IANA from University of Southern California. So the summer of 1998 was kind of interesting. What we thought, we who worked on this, we thought that it would take about 2 years before US government contract with ICANN would actually terminate. And one of the things we can mention is that on the Department of Commerce side of all of this work, the person that wrote all this contract was Karen Rose, that is now a board member of Netnod. So in September 29, the MOU expired and replaced by a joint project agreement. This is 2009, 10 years later. Anyways. And then in 2012 and 2013, under the previous administration in the US, a lot of various bills were passed, and basically we wanted this contract to expire. And then we had the wicket in Dubai in December 2012. There was a Swedish delegation, recognized Maria, recognized me, but also Iran. This was when some states, even though we had this decision in the Human Rights Council, there was a push from some countries that the internet should be ruled by the ITU, by the United Nations, and by states. And they should promise each other, states, that illegal content whatever that is, should be removed from the internet. We, Sweden and others objected, and in the midst of all of this discussion, Iran, this is what the yellow flag with this black square, that means that you request voting. So Iran requested voting, and that stops the discussion in the UN. And suddenly, no more discussion, voting. And we felt from Swedish side, this was plan B. We were the ones that were supposed to request voting, but now we didn't have to. Cool. So there was some voting, and 89 countries signed. This is the first time since ITU was created that not everyone signed. The red countries did not sign. The black did sign. So the black countries here, they are the ones that wanted governments to promise rather to create legislation that would remove bad content from the internet, without defining what bad was. The red countries decided not to sign, and this is where we are. So what then happened was that there was a statement to accelerate this transition, and in March 10, the proposals were passed to the US government on actually removing ICANN from the US government. And we, of course, had an upcoming election in the US, and of course, what is now happening in the US was something that we envisioned. So this was me and Alyssa. Alyssa now being the chair of the IETF, really good person. I'm so happy that she is now the chair of the IETF. So normally, she was the one having headache, but this I had. Anyways. So NTIA, US government said, okay, this proposal is good. We're going to terminate the contract. You kids, you get the car keys. Everything is fine. But then a domestic battle started in the US, and the Republicans, and Ted Cruz specifically, tried to stop this because the Republicans in the US wanted to still control the internet. The federal government was ultimately sued. Okay. And finally, on September 13, here. So the government was sued, it was brought up in court, and they decided, as you see, they were thinking between 4:26 and 4:30. The court were thinking for 4 minutes. And they had to make this decision before October 1st, because October 1st the contract would be automatically extended. So yes, I was awake until midnight. Kind of scary. But it was here decided that the Ted Cruz and the Republicans suing the Democratic Obama administration failed. It was turned down. So finally, in September 30, 2016, the contract expired, and there is no connection between the US government and the current running of internet anymore. Thank you. That was a lot of work. And note that Karen Rose, in 1998, thought it would take 2 years. She was wrong. Anyways, so where are we in Sweden? So these are the two core legislations we have. We have Tryckfrihetsförordningen, was created in 1766. As I said, it was downgraded until 1845. Today's legislation is from 1950. Tryckfrihetsförordning is about printed media, really printed on paper. Okay? We talk about books, newspapers. And this talks about the ability to also access information from public services. There are some exceptions in this legislation, for example, with child abuse. And it does not allow commitment of crime to get hand of the information. But otherwise, this is what gives us the ability to spread information in print. Then we have Yttrandefrihetsgrundlagen, which talks about the ability to express ourselves. It is very similar to Tryckfrihetsgrundlagen, but it is not about print. This is unfortunately only about expressing views in radio, TV, and video. And radio, TV, and video are very interesting, is defined in a very interesting way. That TV, for example, is something that has to be both TV and radio should be linear programming, it should be broadcast, and it is tied to the licensing that some TV and radio channels get to be able to broadcast in the terrestrial network. So this is only about broadcasting in the terrestrial network, not over the internet. Okay? And this covers everything from ads and protection on whatever. It also talks about web pages and access to databases, believe it or not. So web pages are very much as access to a database. There's also something that's called on-demand TV. And on-demand has also a couple of different kind of requirements. For example, there must be a catalog, there must be a listing, there must be all different kind of things. So some of the on-demand things are sort of that we're doing, like in YouTube and others, are not covered either under yttrandefrihetsgrundlagen. So there are some special sort of exceptions for broadcast terrestrial radio and TV. If they are sending over the internet, the same rules does not apply. It is linked to, as I said, the broadcasting license for public service. Whistleblower issues, which is the third thing that is just added, that's a labor law issue. So whistleblower thing that we have added has nothing to do with either of these two. This is actually just a labor legislation issue. We are at the moment, there is now starting up a new media investigation that is looking at the definition of TV and radio. And this is something that I encourage everyone to keep their eyes on, because the definition of, as I said, definition of TV and radio today is tied to broadcast in the terrestrial network for public service and TV4 and others, not over the internet. So this is something that is really important to keep track of. So we do have legislation, including the Constitution, but it is terribly old, and it absolutely requires modernization. I was thinking of today to have a discussion about what is TV. That could have been fun. But on the other hand, because no one really knows. But the problem is that the investigation has now started and no one really wanted to be here on stage. It's much more important that we need to run our formal process here in Sweden, and they will come out. So maybe next meeting or in a year, it could be interesting to have a look at and have a discussion specifically in this room about what is TV. Because if you ask the people actually doing radio and TV, they have a specific view, and I think people in this room, including the one coming from the Swedish Public Broadcasting Corporation and others, we might have a different view than them. So let's wait a year and talk more about that. Thank you.
So a huge expanse of time covered in that presentation. We've got some time left. Any questions for Paf while you have him here in the flesh? Anything not clear?
I'll be with you tonight and tomorrow as well. So.
Yep.
Yeah.
Any informal questions? Formal, informal for Paf? Okay. Well, thanks once again for a fantastic presentation. Cheers. So, theme of the day is time, I suppose. And again, we're running a little bit quick. Another theme of the day. I believe that the coffee is actually served. So I suggest that we adjourn for an early coffee break and meet back here at, what time was the next session starting? 3:15? Sorry, 4. I think it is definitely time for coffee. Meet back here at 4:15. Thank you very much.